Hi all, this is Abe from B351 with another B-side for you guys. Today I'm going to be using the minimax algorithm to play a game called Hex. First, let me tell you a little bit about Hex. Hex is a game that's been popular among mathematicians and game theorists for quite some time. It was independently invented in the 1940s by Pete Hayne and John Nash. Hex uses an n by n board of hexagons, arranged so that each cell is adjacent to 6 other cells. Player 0 tries to make an uninterrupted line of red cells from the top to the bottom of the board, and player 1 tries to make an uninterrupted line of blue cells from the left to the right of the board. There are two key patterns that are central to the strategy of Hex. The first is bridges. Bridges are formed when there are two different ways to connect two cells, as shown here. If red plays in cell B, then blue can play in cell D, and vice versa. Because of that, for the purposes of the game's strategy, blue has actually already connected squares A and C. Note that if blue allows red to play in both B and D, then the bridge is lost, so it has to watch out. The other pattern is edges. Edges are formed when a player has two different ways to reach their goal edge. If red plays in A, blue can play in B, and vice versa. So, like before, for the purposes of the game's strategy, blue is already touching its goal edge. Now I'd like to outline my approach to an implementation of minimax for the game of Hex. I'm using an architecture a little bit different from the one in your A4 assignment. Instead of maintaining separate board, player, and game classes, I use a single class that keeps track of the game state, including its strategic interpretation. I've written a lot of the messier code already, including the undo move, make move, and check game over functions, in order to let you focus on the minimax logic. Undo move and make move keep track of the bridges and edges currently on the board for each player. One thing I'd like to mention is that this architecture allows us to make and undo moves as we traverse the tree, like your Sudoku solvers, instead of generating and duplicating a huge number of classes, like your A3 and A4 assignments. Because of this, it is essential that undo move leaves the board exactly as it was before make move was called. The heuristic function here evaluates the board based on the current player, the number of bridges each player has, and the number of edges each player has. I do this by creating a score for each player as a function of whether it is their turn, the number of bridges they have, and the number of edges they have. I take a root of the number of edges each player has because it's good for them to have one or two, but not helpful to have a whole line of cells around the edge. Then I just give weights to each of these quantities and add them up to get a score. The specific weights are up to you. You could also score the players on the arrangement of their bridges, but that's much more expensive than what we have right now, so you might need to optimize your code significantly. Finally, I take player 0's score and subtract player 1's score to get the heuristic value. It is extremely common for heuristics to take the form of the difference between two players' scores. Now let's talk about the minimax algorithm. The purpose of the minimax algorithm is to logically determine how much a certain position favors player 0, and to return that as a numerical score. If it also returns the best move at each state, then it can be used as a strategy for picking moves. In this framework, minimax is expected to return a move, score tuple. The first step in evaluating a game state is to check whether or not it is terminal. In this program, make move sets terminal to -1 if the last move did not end the game, 0 if the last move resulted in a victory for player 0, and 1 if the last move resulted in a victory for player 1. So then we return a very large positive value if terminal is 0, and a very large negative value if terminal is 1. I multiply these values by the remaining depth plus 1, so that the AI will always pursue the fastest path to victory. I would strongly recommend implementing that in your code as well. Then, we check if the depth is 0. If so, we can't expand anymore. It's time to return our heuristic value for the current state. In these situations where we aren't investigating any moves, we can just return none for our best move. Now we generate the children of the current state, and we iterate over them. We score each child by recursively calling minimax again with depth -1. On the homework, you will also pass the generated child boards to minimax, but in this problem, the trick is that you have to undo each move after scoring it. Then we keep track of the move with the highest score if it's player 0's turn, and the move with the lowest score if it's player 1's turn. Finally, we return the best move for the current player and its score. Alpha-beta pruning can be quite tricky, but I've done my best to explain it as clearly as I can. Alpha is a variable that keeps track of the highest score move that player 0, max, has encountered, and beta is a variable that keeps track of the lowest score move that player 1, min, has encountered. For example, after evaluating the move to the left, max knows that they have a path that results in a score of 3, and we store that as our alpha value. Then, as min is expanding the children of node B, as soon as he evaluates the orange node with score 1, it knows that it has a path that results in a score of 1, and we store that as our beta value. At this point, our best value for B is already less than or equal to alpha, and so we know that max will not choose B, because it has a better path elsewhere. That's the intuition behind alpha-beta pruning. So the difference in the alpha-beta algorithm compared to normal minimax is that we're keeping track of our alpha and beta values and passing them in our recursion calls. During player 0's turn, we update alpha to always be the highest score player 0 has found so far, and then if the alpha is greater than or equal to beta, we break, because player 1 will not allow the current state to be reached. And likewise, player 1 updates beta to be the lowest score they have found so far, and if beta is less than or equal to alpha, we break, because player 0 will not allow the current state to be reached. Finally, we return the best move for the current player, along with its score. In this project, I'm not implementing dynamic programming because it's not well suited to this particular framework. Dynamic programming can be used to cache values for the heuristic, or it could be more elaborately used to sort the possible moves to optimize alpha-beta pruning. Here, our heuristic is very cheap, so we don't gain much by caching it, and it's quite difficult to sort possible moves by their heuristic values. That said, it is quite easy to calculate a hash of the current game state, and in case you wanted to play around with dynamic programming concepts, I've included a solution file that calculates hashes for you to work with. A simple example of what you could do to implement dynamic programming here would be to set up your program to cache, or memorize, its heuristic values. Then you would modify your heuristic function to first check if the heuristic for the current hash has already been calculated, and return the memorized value if so. Otherwise, you would calculate it as usual and then add it to your dictionary of memorized values, and then finally return it. Now that we've talked through all of the ideas behind the minimax and alpha-beta algorithms, you have all of the tools you need to write a solution to this problem. I would advise pausing the video now and getting started on your solution. Afterwards, you can consult the rest of the video if you have any questions or issues. To code the heuristic function, we start by calculating our P0 score, based on the number of P0 bridges there are, the number of P0 edges there are, and whether or not it's player 0's turn. We set up something symmetric for player 1, and then return their difference as our heuristic score. For minimax, we first check whether or not the current state is terminal, and if so, we return no move and a score of 1000 times the remaining depth if player 0 won, and negative 1000 times the remaining depth if player 1 won. Right, that's actually 1000 times the remaining depth plus 1, so that even if there are no moves left, it will still return a very high score, and the same for if player 1 won. Then we return the heuristic value if the depth is 0. Now we start to evaluate possible moves. We make the move, then we score the resulting state, and then we undo the move. If we don't have a best move yet, or if this is the best move, the highest for player 0 and the lowest for player 1, then we save it as the best move and save its score as the best score. And then once we've looked at all of the possibilities, we return the best move and its score as a tuple. Now alpha-beta proceeds similarly, but once we start maximizing or minimizing moves, we have to be a little bit careful. First off, when we score our children, we have to pass the alpha-beta function our alpha and beta values. Then, as we evaluate moves, we separate our cases for player 0 and player 1. When we see a new best move for player 0, we update alpha if it is the best move it has encountered so far. If it is, then we check whether its score is higher than the beta value, the player 1's best move so far. If so, player 1 will not allow this state to be reached, and we can stop considering additional children. The code for player 1 is pretty much analogous. Whenever we find a new best move for min, then we check whether or not it is a new beta value. If so, then we check whether or not it is worse for player 0 than the best path so far, the alpha value. If so, then max will not allow this state to occur, and we can break. We return the best move for the current player, along with its score. And that's it for the code. I hope this video was helpful and fun for you. If you want to work more with hex for your final project, that would definitely be a fun and valid option for you, though I would recommend that you build a new framework from scratch. If you have any questions for me about this game, or any questions at all about the minimax or alpha-beta algorithms, please feel free to come to our office hours or reach out on Piazza. Best of luck with your homework.